Hello everyone, welcome to Medivice. This video is dedicated to the topic of types of hemoglobin. So let's start. So there are two types of hemoglobin that you are going to encounter. We have the physiological and the pathological types. There are three types of physiological hemoglobin seen: the embryonic, fetal, and adult hemoglobin. So now what are the names of each of these hemoglobin types? So there are three types of embryonic hemoglobin: hemoglobin Gower 1, hemoglobin Gower 2, and hemoglobin Portland. This can be asked as a one-liner. Fetal hemoglobin is very easy to remember. We just have HbF. Adult hemoglobin is also easy to remember. We have HbA1 and HbA2. What is important to remember are the chains that are in each of these hemoglobin, which is what we're going to see in a while. Now, there are a lot of pathological types of hemoglobin. We have HbS, HbC, Bart's hemoglobin, HbH, carboxyhemoglobin, methemoglobin, and many more. But for now, we're mainly going to be seeing the physiological types of hemoglobin and HbS and HbC. I will be making a detailed video on every hemoglobinopathy, so make sure to check those out. But for now, let's just see the physiological types of hemoglobin and their chains. So the hemoglobin Gower 1 has two epsilon chains and two zeta chains. Hemoglobin Gower 2 has two alpha chains and two epsilon chains. HB Portland has two gamma chains and two zeta chains. HbF, which is important to remember, has two alpha chains and two gamma chains. HbA1 has two alpha, two beta, and HbA2 has two alpha and two gamma. Note that the fetal hemoglobin and both the types of adult hemoglobin have alpha chains. So the first three, as we saw, are seen in the embryonic life. HbF is fetal hemoglobin and the last two are adult hemoglobin. Now we also have to look at this graph. This graph tells us about the production of each of these chains according to the timeline. So I'll put these side by side so you can keep on comparing. So first you can see that the zeta chain and the epsilon chain both are very high in the start of the embryonic life but very quickly reduce. And their quantity is almost zero by the 9th or 10th week. This is the reason that you're not going to find these chains in the adult or fetal hemoglobin. The alpha hemoglobin starts production early on and stays constant. Next, you can see that the gamma chains are quite high during the fetal life, meaning the alpha chain and the gamma chain are high during the fetal life. Both of these chains is what makes the fetal hemoglobin. But then the gamma chain decreases after birth. Then the beta hemoglobin is less during the intrauterine life but then increases after birth. So the alpha and beta chains are high after birth and these are what make the A1 hemoglobin. Now you must be thinking, what about HbA2? Where is that? So on the right side of the graph, you can see that there is very less quantity of delta chain. So a combination of alpha chain and this very less delta chain gives us HbA2, which is why out of all of the hemoglobin in a human body, only about 2 or 3% is contributed by HbA2. In fact, let us look at the exact percentages. So in an adult, 97% of the total hemoglobin is HbA1. And this is proved from the graph where we can see that the alpha chain and the beta chain is very high. Then HbA2 is only about 2%. Why? Because we saw that the quantity of delta chain is very less. Also, the fetal hemoglobin is not exactly 0% in an adult, it is about 1%. You can see in the graph that the gamma chain, which contributes to fetal hemoglobin, is not exactly zero after birth. There is still some quantity left. So this makes the HbF. So this was all about the physiological hemoglobin. Now let's take a look at the pathological ones. So first of all, we have HbS. So HbS is a type of hemoglobin which is seen in sickle cell anemia. I will be making a detailed video on sickle cell anemia very soon, but let's see the main points for now. So there are two variations seen here. A person can either have sickle cell trait or sickle cell disease. Now what is the difference exactly? So sickle cell trait is when a person inherits only one abnormal hemoglobin gene from one parent. Here the shape of the RBC is usually normal and the person does not have a lot of symptoms. But in sickle cell disease, here the person inherits both the abnormal genes from both the parents. So obviously the disease is going to be more severe and most of the RBCs are going to be shaped like a sickle. Let's exactly see what happens in this disease. So here I have hemoglobin. Let's zoom into this part and see what's happening. So here I have taken out the beta chain of the hemoglobin. Now let's start numbering the positions. So normally at the 6th position of the beta chain we have glutamate, but due to the mutation seen, this glutamate is replaced by valine. This change leads to the abnormal shape of the RBCs. So here you can see that normally on the 6th position we have glutamate and this is negatively charged or is polar. Very important to remember because this will be important in the electrophoresis part which is just coming up. And then when it is replaced by valine, this is no longer negatively charged, it is non-polar, so it has no charge. This is abnormal. So very similarly, we have another disease called as HBC disease. So a very similar thing happens here. Here again we have the HBC trait and the HBC disease. So HBC trait is when only one abnormal gene is inherited and the shape of the RBCs are mostly normal. But in the HBC disease, here both the genes are inherited which leads to severe disease. Now let's see what exactly is happening inside the hemoglobin. So again we zoom into the chain and let's see what's happening. So counting the positions, normally you know that we have glutamate on the 6th position. Here instead of valine as seen in HBS, we have lysine. So lysine will come and replace glutamate which will lead to this disease. So normally you already know that it is negatively charged, but here since it is replaced by lysine, it is no longer negatively charged but is positively charged. And you know that if a thing is negatively charged or positively charged, in both cases it is polar. So normally it is negatively charged or polar. HBC is when it is positively charged and is also polar, and HBS is when it is replaced by valine where there is no charge or it is non-polar. Now let's see how each of these will look on electrophoresis. So what exactly do we do in electrophoresis? So we have two rods here. One is called as the cathode and one is called as the anode. So cathode is the negatively charged pole and the positively charged pole is the anode. So what we will do here is that we will put blood. And since the RBCs or the hemoglobin is charged, they should start moving under the influence of these electrodes. So here we have an origin point. So you know that normally hemoglobin is negatively charged. So under the influence of this cathode and anode, this hemoglobin will start moving towards the positively charged pole or anode. Now let's see what happens in the other cases. So to avoid overcrowding, I've removed all of the other things, but for reference you should know that the left side is negatively charged and the right side is positively charged. So what happens when we have adult hemoglobin? So all of the hemoglobin will be moved towards the positive pole and will be collected here. Now let's say a person is suffering from some disease due to which his body has both HbA and HbF. So what is going to happen under this circumstance? So the HbF is not as negatively charged as the normal HbA. Due to this, you will see 2 points. Some of the hemoglobin will be where normally we find HbA, but the HbF will be more towards the negative pole because it is not a very strong negative. Now, what happens in sickle cell trait? So, in sickle cell trait, we have both adult hemoglobin and S hemoglobin. Now, you already know that valine is neutral. So, HbA is negatively charged, but now some of the hemoglobin that we have is not negatively charged. So, again, we are going to get 2 points here. Some of the hemoglobin that is normal will be found where HbA is normally found. But the abnormal hemoglobin, which contains valine, will be more towards the negative pole. And why is that? Because valine is neutral. Now you have to answer this. What happens if a person has sickle cell disease? I'll give you a few seconds to think. Okay, so in this case, almost all of the hemoglobin that the person has will be HbS. Due to this, almost no hemoglobin will be found where Hba is normally there. All of the hemoglobin will be collected at one point, which is more towards the negative pole. Now, similarly, let's see what happens in HbC trait. So here the person will have both HbA and HbC, and you already know that lysine is positive. So what is going to happen here? So some of the hemoglobin that is normal will be found where normally we have HbA, but some of the HbC will be found towards the negative pole. And why is that? This is because the lysine is positive. So this positive lysine will be attracted by the negative pole, and so it will be found very far away from the normal HbA position. Now in HbC disease also, here the person will only have HbC. Due to this, all of the hemoglobin will be collected at one point, which is towards the negative pole. Finally, let's just compare all of these hemoglobin in a single chart. So here we have HbA, then we have HbF and HbA, then we have sickle cell trait where the person has both HbA and HbS. We have HbS or sickle cell disease. We have HbA and HbC, which is HbC trait. And finally, we have HbC or HbC disease. That's it for this video. If you have any doubts, so please leave them in the comments, or you can message me on Instagram anytime. The link to my Instagram is in the description. Thank you.